Oh, yeah.
Prezados, bom dia. Neste momento, seguiremos para a terceira palestra, a nossa segunda palestra internacional da manhã, a ser ministrada pelo professor Leonardo Gordillo. Então, convidamos o professor Leonardo para ministrar essa palestra intitulada Drop Impact Dynamics on Solid Surfaces, Evolution of Impact Force. O professor Leonardo, ele é professor adjunto do Departamento de Física da Universidade Santiago do Chile desde 2017. O professor Leonardo obteve sua graduação como astrônomo pela Pontifícia Universidade Católica do Chile em 2005. É mestre em Mecânica dos Fluidos pela Universidade Pierre-Marie Curie, na França, e é doutor em Física pela Universidade do Chile. Ele possui pós-doutorado pelo Laboratório de Materiais e Sistemas Complexos da França e pelo Departamento de Engenharia Química e Ciência dos Materiais pela Universidade de Minnesota. O seu campo de pesquisa é a dinâmica dos fluidos, com foco em interfaces, gotas, ondas, instabilidade hidrodinâmica e fenômenos não lineares, bem como técnicas experimentais. Então, agora eu passo a palavra para o professor Leonardo.
Okay. Well, thank you, Leticia, for your kind invitation for this conference. So I hope that this presentation goes as well. So I'm going to talk today about a work that I did as a postdoc when I was in my second postdoc in the University of Minnesota. In the Chemical Engineering and Material Science department. So this is a work that was done under the supervision of Shang Cheng and with the collaboration of Tim Pisu, which is doing his postdoc, his PhD at this university. So today I'm going to talk about something that is a very simple idea, but it was not very deeply understood as a few years ago when we tried to do these measurements, and also after some theoretical results that were obtained in France a few years before. So although this is a quite simple idea, it's very nice to see how this phenomena was not completely understood until a very recent time. So let's talk a little bit about how all this started. So I know that many of you are young students, and one thing that one usually learns when you start to do research is that research is not usually driving on a straight road. Usually you start with a subject, and very often you find that the subject maybe needs to do a different kind of approach. So this is how this started. And it's very nice because we started with a very complicated problem that my supervisor in Minnesota, Shang Chen, was interested in. And I will tell you in a minute which were the reasons why we were interested in doing this. So what was the main question at the beginning of our research was, what happens with crater formation due to liquid impact on a sun surface? And this is a very interesting question because a lot of people have been doing research on this subject, and they have found very interesting similarities with what happens in crater formation in planets. So usually people do two things. I will go in detail in a minute about that, but usually they throw whether solid spheres on a sand bed, right, and they see what are the shape of the craters that are formed, whether they try liquid droplets, usually water droplets, and then they see another kind of behavior, and then they compare these and they start to get some conclusions about that. So the first question that we had was, well, what happens if we try to look to the transition between these two behaviors, right? You can imagine that on one hand you have a solid sphere, they don't deform at all, and on the other side you have a liquid sphere that deforms a lot. And then a natural way to go through this transition, the thing that we thought at that point was, okay, what happens if we modify the viscosity of the drop as we increase and do different trials on different sand beds? And this is what we got. So these are videos that we recorded. So on the left-hand side, on the top, you have a very thin drop, 5 centistokes, that is very similar to what you have in water. And then you start to increase the viscosity to the right, then you have 10 times more viscosity of the liquid in the second impact, and then you continue increasing until you arrive to almost more than 10,000 times the viscosity of the water. Okay, this is the last one is a very thick drop. And what you can observe is that when the drop impacts the crater, you have a very different kind of behavior. In the first case, the drop is so thin that then you have a lot of emergence of tiny drops after the impact. And then as you start to increase these, then you see what we wanted, what we expected at the beginning, right? That then you have that the droplets is thicker, so it's harder to deform. And then at the end, in the thickest drop, you don't see almost any deformation of the drop. So we expected that this very thick drop was going to be very similar to to what happens when you throw a solid sphere, right, with no deformation. And then we started to, try to get some conclusions. So, but the problem is that in these original experiments, you have a lot of parameters to adjust with, and we try to find a way to plot all our results in a single drop, in a single figure. And we were trying to look to these scaling laws, right? We were trying to plot what was going to be the diameter of the droplet, right? This is plotted in the y-axis in terms of several parameters of the problem. So you can imagine what are the parameters. You have viscosity that is related to the Reynolds number. You have a surface tension that is related to the Weber number. You have inertia versus gravity that is related to the Froude number. And then you have, of course, the size of the droplet with respect to the other quantity that appears in the problem, which is the size of the grains. So we were doing this, and we had, you can't imagine how many months we were trying these experiments. We made a massive experimental service. We had several undergraduate students that were doing, the hard work of just throwing these tiny droplets into the sandbed. And at the end, we had like 6,000 experiments. Okay, and just to give you an idea, this is twice the number of craters that you can find in Moon, Mars, and Mercury that are larger than 100 meters. So this is really a lot of data, and we were really working very hard in order to find how we could make all these points collapse into a single plot. So we were trying to prepare this plot, and we were trying to put the solid sphere limit. Remember, this is very high viscosity, right? Very low Reynolds number. So we had this slope here that matches what you find in experiments with solid spheres. And then you had this other limit that is on the top, that was the liquid sphere limits, which has a slightly small slope, a smaller slope. And we were pretty happy with that. But, something that the reason why we were interested in doing this was basically because the liquid sphere limit is what people usually see in planetary craters. So there have been many experiments, mainly in the last 50 years of the past decade, where they made these explosions in the middle of the desert in order to see what was the size of the crater as a function of the energy that they were putting in these explosions. And they found that this dependence was a scaling law with this exponent that goes as m to the 0.6. So we were motivated by this, but the problem is that we had so many parameters, and we were trying to combine all these parameters into a single number that could collapse all our points in one single curve. And I already told you, these parameters are viscosity, surface tension, drop size, the velocity of the drop that is hidden in the Froude number, the density of the liquid too, okay, the grain size also, and also the grain density. So if you combine these parameters, you can really build a lot of dimensionless parameters, and then it's really hard to understand how we can combine them, even though we have a huge amount of experimental data. So we spent, imagine, 6,000 craters. That is a lot of effort, and we spent a lot of time doing that. And in the meantime, while the experiments were done, we found ourselves with plenty of time to rethink how could we drive this experiment into some results that could be useful. And then So at some point, I asked my supervisor, Shang Cheng, at that time, what happens if we do something simpler? I mean, the sand is really making a lot of problems. It's a way, somehow we think that the crater size should depend on how hard our drop is, right? If we think about liquid drops, solid drops, thicker drops, and thinner drops, then we can think that as much as the drop deforms, then that will mean that the drop will be somehow softer. And then we completely think about, we completely redesign this experiment. And the problem, another problem of these experiments besides the sand is the drop impact itself. It's a very hard problem to study. And it's something that in the last years, many people have been devoting time. And it's a pretty tough problem, very complicated. And we are, researchers are understanding this problem like by parts. And if you want to make a short summary of what happens when a drop impacts a solid surface, then what you have is that there are, let's say, more or less 4 stages. The first one will be the initial contacts. That is when the drop just barely touches the substrate, so it happens in a very short time. Then you have a second stage, a second regime that will be spreading. Okay, now the drop is already smashed against the substrate, and then it's deforming. You have large deformations. And then at some point you have what is the maximal spreading. So at some point the drop will stop expanding, as you can see in the video on the top. And then at the end you will have, after the maximal spreading, depending on your parameters, then the drop will start to retract, and it may even bounce. It may even completely dry like a pancake. There are many possible outcomes from this last regime. And if you analyze what the progress in each of these fields, and then you will see that initial contact, the very first part of what happens when a drop touches the substrate, is recently understood. It's not a very, this is something that we really contributed. I hope that at the end of this presentation, you will have a rough idea what happens during the first seconds during the first times of the impact. The spreading, on the other hand, there have been many progress in the last year, so a lot of things have been already understood from this, and this is something that is still a very rich mine where you can do research. And then you have maximal spreading, because this is when the drop starts to become slower. You can imagine that the drop very fast hits the surface, it immediately starts to expand, and at some point it reaches the maximal spreading. And the maximal spreading is probably the classical research that has been done in the last decades for drop impact, even very early from the very first images that the British researcher Worthington made at the beginning. He was able to capture the maximal spreading, because the maximal spreading is, this is the slowest part of the impact, right? When the drop attains its maximal diameter. And then there is also some research about retraction, that what happens after this maximal spreading. The problem here, this is still a very rich field, not because it's hard to measure it, but mainly because there are so many possible outcomes. So you have bounds, and you may have fingers. There are so many things that happen during the retraction that is still a very interesting stage of drop impact to study. What happens if we think about these different stages in terms of experiments? So maximal spreading, you can use imaging, and then you can even use classical imaging. And I told you a few seconds ago that Worthington made the first images of drop spreading using a very, very old camera. Worthington, these works were from the end of the 19th century. So he was basically using magnesium to flash the drop impact, and he was using photographic paper to notice what was the maximal spreading when a drop impacts a surface. Then retraction also is usually not as fast as when the drop hits, so imaging also usually works very well for retraction. And then they are even used for advertisement. If you go to the internet and you just write in Google drop impact, you will see all these beautiful images of grounds and all these fingers that emerge during drop impact. Okay, and the problem with imaging, you can already take a lot of information, is that you don't have many access about what is the velocity field inside the drop. You have just the shape of the interface. So that will be something that unfortunately was not very accessible when only imaging was done. And then we had a lot of, especially in the last decades, we have a lot of numerical simulations that now they can access. So compared to experiments, numerical simulations have the advantage that you can reach all this information concerning what is the velocity field inside the drop. And that means getting not only the velocity field, but also the curvature of the interface that is really hard to measure, and also the pressure. But what happens, what is the challenge when you are dealing with the initial contact, right? This is when the drop touches the surface. So basically, these are the pictures that Worthington made in the end of the 19th century. So these were the sketches done by hand, but he obtained these by after some old style imaging, right? So this is what he observed. He observes that then he has the drop touching the interface. This is how he felt this process was going on. And at the very beginning, he had this beautiful idea that the drop barely deforms at the beginning. You can see exactly the same in the modern video on the top, right? So when the drop touches, then the upper part of the drop is like the drop doesn't know that it still has heat, right? So only the bottom is deforming, and the upper part is still keeping its spherical shape. You can see that in the top video. Okay, and then it's really hard to make imaging here because this is happening so fast. Remember that maximal spreading is already when these things have slowed down. When the drop touches, this can be really a very fast system. And again, the interface is not deformed, so we don't have too many information about what's going inside. And then one natural way of doing this is through pressure measurements. Okay, and then for the spreading final regime, what you can do for the intermediate regime, sorry for that, what you can do is something in between. Okay, so spreading will be a good stage where you can do both pressure measurements and also imaging. Okay, sort of like in between something that is happening very fast and something that is already slow, so you can make some deformations. And in the spreading, also you can start to see some deformation of the interface, so you can have get some interesting conclusions about that. Okay, so let's talk about force exerted by a drop during impact. Okay, so you can imagine what happens when a drop touches a substrate, right? Somehow it has to exert some force on it. So these are some measurements that were done in 2014. So what you can see on the screen on the pictures is this force sensor that is just below a glass plate, and then the force hits the surface, and then what you can see in the first plot on the left is the force against time. And when you can see what this group in France observes is that you have originally a fast rise, and then you have a slow decay. And then this same group in France, they try to understand if there could be some kind of a scaling law. They only tried water, and what they observe is that there is some kind of a law that relates the velocity of the drop with the force. This is very simple dimensional analysis. You can even do that when you are, in the first year of your science or engineering studies. You can obtain that the force should go as a product of the density, the square of the radius, and the square of the velocity. And this law collapses very well what they observed. But then, you can have this law, right? And you can understand how much is the force that the drop exerts. But the next question that naturally arises is, can the force evolution, how the force depends on time, could this reveal something about the underlying physics of the first initial regime? And this is mainly the question that we pose ourselves. And we found also these beautiful numerical simulations that were obtained in 2010, also by a group in France, an independent group. And they were, plotting, they have the very, expensive simulation with a lot of cores running in order to calculate this. So they basically were doing the same experiments. They were hitting a liquid droplet on a solid substrate. And what they observed, here's what I'm plotting, is the pressure field. And you can see there is something that is very nice from this figure, and they realized about that, is that if you see the color scheme that are in this, that can be seen in this figure, you will see that the color scheme, it doesn't look like it's changing too much. Actually, it's just growing, right? So it looks like it's expanding on the horizontal axis and on the vertical axis with some low, but the structure is more or less the same. You can see that it's darker on the left, that it's lighter on the right, and it decreases as you go higher. And this is the signature of something that in physics we call a self-similar field, right? That something that is scaling in time with some given law. So there is this other beautiful work from another group in France that it was in the same level. It's completely independent people that inspired on Wagner theory, that is work from the 30s, very old works. Wagner was interested in understanding what happens when these hydroplanes land, or I should not say land, maybe water, on the ocean. What are the forces that are exerted by the ocean on the parts of the plane? Then they had some interesting results. And you can invert this problem, and instead of thinking of an airplane hitting the sea, you can think also of a droplet hitting a solid substrate. And this is basically what they do. They did in 2016's work. And what they obtain is that the pressure field should behave in this way. And you can see that there is a very nice singularity when r equals the square root of 3 multiplied by t, which is basically what gives this darker color in the upper picture. And then you can also, of course, integrate the pressure on the bottom, the normal pressure, and then you can get a nice law for the force. And this is in viscid approximation. They don't consider any viscosity, and what they obtain is this beautiful law for the force. So they basically predicted that after the force touches the substrate, there should be a square root growth of the force as a function of time, with, of course, some other dependence on the other factors. Okay, and this is just, I want just to show you a little bit about the equation. This is a very special type of self-similarity. It's not a simpler one. So you can see here that in the results they obtain, what they say is that the pressure is a function of two self-similar variables that grow as a square root of time. This is, you can see big P depends on R divided by a square root of time and Z divided by a square root of time. And the pressure itself is also a function, it also decreases as a square root of time. So that means that for shorter time, you will have higher pressures, right? And then, well, they plug these into different quantities involved in the problem. Phi is the potential, the velocity potential. H will be the height of the region that where you have self-similarity, and the variable D will be the point where the drop, where you have the triple contact line, right? Where you have the drop, the solid, and the air advancing. When you do that and you plug all these, this is not easy math, but it's still understandable. Very nice results. You have this problem that you can solve. You have basically the Laplace equation. You can get the pressure inside the velocity field. And finally, after some calculations, you can get the pressure in terms of time. And this is giving you the scaling law that they predicted by hand. These are results from their numerical simulation. And if you get these results for the pressure, you can integrate and obtain the force, and you also get what they observe. Notice that this is valid only for a window of time that is much smaller than 1. The axes are already non-dimensionless variables, so this means that this is valid only for a very short time, right at the beginning when the drop impacts the surface. Okay, so let's talk a little bit. Let's talk about experiments. So we have these results in hand, and we wanted to see what happens if we start to plug viscosity in the problem, right? All these people in France studied what happens when you have liquid droplets. They already have a nice scaling law for the maximal force, but what happens when viscosity is included in this problem? And then we were doing measurements already. We wanted to understand what happens with the sandbed, and then we had high-speed camera. We bought this force sensor that is very sensitive, that allow us to record the force when the drop hits the surface. And what you can see there is the results for different viscosity. So this is basically the same picture that you had at the beginning with the sand beds with the difference that we took away the sampling, and now we are putting this beautiful force sensor that allow us to measure the force in terms of time. So what can you observe from this? All these droplets are more or less of the same diameter. You can see that the drops on the right are much thicker. They are almost 30,000 times the impact of the viscosity of water. They are so thick that they do not have this typical round shape that you will expect for a drop. That is because it's so viscous that the time that we have from the point where they are released from the needle and the point they hit the surface is not enough to attain its equilibrium shape of spherical equilibrium shape. And what can you observe is what we already somehow knew, right? That the thicker the drop, the larger the force. You can see that the force curve is larger on the right side, and also that the impact is happening faster, right? You can see that everything is happening in a shorter time scale as you increase the viscosity. On the lower line, what you have is something that we obtain through imaging. So you have the position of the triple contact line, that will be the green curves, R0, and you can see that, of course, for thicker drops, you don't have, they very fast they attain a stable value for these radius of contact. And then you have also the blue line. The blue line will be the height at the center of the drop. Okay, and then you can also see, of course, that the thicker the drop, the smaller is the deformation. Okay, so let's see what happens with a typical impact. So here on the top plot, we have, again, this is basically the same information that you had in the previous figure, but in detail. But here you have the maximal height and the contact radius, right? And there you also have some simple lines that somehow show what happens. I want also to show that there is this light blue dashed line that it represents 1 minus tau, right? 1 minus tau is just the ballistic motion, right? It's just what happens if the drop will continue going down and there is no solid surface to impact. And you can see that the drop in impact happens at 0, and there is still a not very small window of time, right? The gray window, where basically the top part that is represented here by H max that has no idea the impact already happened, right? It just continue moving down as there is no any impact, any solid surface. Then you also have a prediction, that is the prediction obtained by this group in France of the work of them that I described, that is that the contact radius should behave as this. So that means that what we are observing in experiment matches what they observed, what they predicted for a pretty large time. Okay, you can see that the two curves are just mainly one on top of the other. And then the green curve is something that we're going to describe in a few minutes. That is what is the deformation of the boundary layer. Okay. On the bottom figure, what you have is the force against time. You already saw that, and I included what happens with the drop. Some images, and you can again see the signature of the drop going down and not knowing that there is a solid surface on the bottom is basically having all its points, all the shape of the drop not being affected by the drop. So you can see that right before the dashed the gray area, you will see that the drop is not only falling with the ballistic law, but also keeping exactly its spherical shape. And only after that, you will see that the curvature on the top will start to deform. Okay, there are also some comparisons with other works that you can find in the literature if you are interested. Okay, so well, of course, we used already dimensionless versions of these quantities on the x-axis and on the y-axis, so then we can collapse our different sets of data. Okay, let's talk about force characterization. This is again the same results, but plotted for different viscosity, just on top of the other. You can see now, this is clearer than the thicker drops. The number here, the different curves correspond to different viscosity. You will see thicker drops are giving larger forces than thinner drops. Okay, and also the impact is happening in shorter times. Okay, and this is what you can see on the left. And on the right, what we tried is what happens if we use what people predicted, that is that the force at t equals 0 will behave more or less as a square root of time. So basically what we did is we multiplied the force by 1 divided by a square root of time. And then we also we multiplied by some Reynolds number in order to increase the span a little bit of the curves. What you observe is that the larger is the Reynolds number, that means the thinner is the drop, then it is quite good, the approximation of this French group, right? You see that for shorter times, these curves start to become a flat surface. And that means that their predictions is pretty right. The problem is that when you start to increase viscosity, you will see this in the purple curves. As you start to increase them, this curve doesn't start to not go into a constant value, which means that maybe that this dependence is not as correct as we expect. Okay, so this shows that basically at the very beginning we have a square root time behavior, just what these people showed. Okay, what happens next? Okay, the other thing that we try to do is what is the early time coefficient, right? The early time coefficient will be, if you see this tiny yellow plot on the right plot, you will see that the prediction was that the force behaves as some constant multiplied by the dimensionless time with an exponent of some value beta that we need to determine. So we prepare these two plots. On the right hand, you have a plot for beta, right, for what is the exponent, and on the left plot you have a plot for alpha. So first thing, as we already somehow knew from the previous plot, we see that the larger the Reynolds number, it seems that beta is going to a constant, and this constant is 1/2. So this shows that the square root time law for the impact is pretty accurate. It works really well, and it works really well even though the Reynolds number can be low. You can see that it works well even for a Reynolds number equal to 1. Okay, that means drops that are still already very viscous. And on the left-hand side, you have the same figure, but now for the prefactor, right? Instead of plotting beta, now what we are is plotting alpha. And when we do that, then we see that alpha is going to a constant for very large values, but this constant changes as the Reynolds number decreases, right? And unfortunately, it's not as nice as beta. So beta is always behaving like 1/2, but the factor is not behaving as what is expected from the theory, which is the black dotted line that is plotted there and is given by this constant found by this group. So, okay, that means that the prefactor probably should be somehow adapted. On the inside of this plot also, we plot what happens if we take alpha, we subtract this asymptotic value for high Reynolds number, and what we see is that it seems that the power law of alpha minus the asymptotic value goes as a square root of as 1 divided by a square root of Reynolds number. Okay, so then the question is, I mean, we have some results for the inviscid case. Now we have measurements that confirm that the inviscid case works really well. Now the next question is, can we get something for the viscous case, right? We wanted to study what happens when the drops start to become thicker. And there is a very nice way to obtain what are the scaling laws for early times when in viscid case and also for viscid case. So let's do a very simple momentum balance. Okay, what you can get there on the left, on the denominator, sorry, on the numerator on the right is the change of momentum. Okay, so it's basically the mass that is rho multiplied by the volume, and this is multiplied by the velocity, right? The drop arises to the surface with some given velocity u0, right? The velocity of the impact, and then suddenly this velocity goes to 0, right? So then the change of momentum should be that. And then we make this, old balance of impulse, right? That is time multiplied by force, and on the right you have momentum change, and what you get is this. And then the next question is, what is the volume? And what we have seen from the experiments is that the volume is not the full volume of the drop, but is some kind of at the very beginning, some kind of region that is growing in time. And when you do that, then you can estimate the volume as the R0 squared multiplied by some distance d, right? That is the distance that the drop has somehow, let's say, penetrated into the solid. And when you replace this in the formula, then what you obtain is this force equation. Okay, of course we don't need to have the factors, but these, hand-waving argument already gives you that the force should behave as a square root of time. Then the question is, what happens? This is all done by assuming that there is no viscosity. Now, what happens when we include viscosity? Then we can also try to make some balance. Then you have here the work made by some given force, and then on the right hand you have some kind of the force per unit of volume, right, given by the shear stress of the fluid. And then we multiplied this again by using the same idea that we have on the top, by the volume that is involved in the experiment. And we have this formula. And the problem is that we need some length scale for the variation of the velocity, right? And then we have many length scales in the problem that we can think about too. One will be a length scale related to how much the droplet will have penetrated into the solid, just as we did before. And then that will give us a force that should be proportional to the square root of time, and also, but with a prefactor that goes as 1 divided by Reynolds number. On the other hand, we can also think about length scale that is not given by this quantity, but by this other that many people probably that has studied boundary layers can identify very well. This is something related to the viscosity. And we plug here the time after the impact. And when we do that, then we have a force that again has a scaling law that goes as a square root of time, but that the prefactor is not going anymore as 1 divided by Reynolds number, but 1 divided by Reynolds number, square root of Reynolds number. So then both cases, same behavior. We need actually to see what will happen with the prefactor, right? And then the prefactor will let us maybe understand what happens when these kind of balances are done. Okay, so that's basically what we already plotted in that figure. Sorry for that. Okay, this group in France also made a few things about boundary layers. So they already, sorry, my printer started to clean itself in a very bad moment, but it will stop very soon. So I hope that you can still hear me well. So this group in France also made a little thing about the boundary layer solution. Okay, they found, this is some calculations that they did, and you can also, in the same way that you have envisage a region that is growing as a function of time, you also may have a boundary layer that is also growing as a function of time. And they have this nice formula for the radial velocity, and then also again with some kind of cell-similar variable. And if you do that, then you can do some asymptotic matching in terms of this epsilon value. That will be the parameter at which we are doing expansion. We're assuming high Reynolds number expansion, so we are looking for first correction for the Reynolds number. You can do that for the horizontal velocity, radial velocity, sorry, and also for the vertical velocity. And then at the end, this is some theoretical work that we did, then you have some kind of matching condition. This is classical boundary layer matching. And then you have expressions for the velocity outside the boundary layer, inside the boundary layer, and after you do all this, and you get some kind of results, and you do some limits. Then at the end, all these, you can find what will be the correction for the velocity. And if you get the correction for the velocity, then you are able to get what will be the force for your problem, your correction for the problem. You plug this at second order in the bulk. You analyze this problem. Actually, the solutions are exactly the same for the first order problem, so you don't need to work that much in order to find new solutions. And then at the end, you get these velocity fields. Okay, so this is a lot of calculations, but you can follow them, and you look for the papers. And you can. It's very nice because in the right plot on the of what I'm showing, you can see what will be the approximation for the first order. That means assuming that the liquid is completely inviscid. And then the orange curve, which was our theoretical results, show that when you add viscosity, then you have a small correction that is happening in a small region. But of course, far from this region behaves as the inviscid solution. Okay, and all these allow us to, sorry, let me move this, allow us to compute what will be the correction for the prefactor in these force measurements. Okay, basically in terms of physics, what does it happen when you have a viscosity? That means that there will be a boundary layer that is formed in the bottom, and this boundary layer will make that these fronts that we discussed at the beginning will start to propagate faster. So if you remember these numerical simulations pictures that were found by this group in France at the very beginning, then you will have that the higher the viscosity, this region will start to grow faster. What happens if we compare now this with our results? Okay, so same pictures as before. Now I'm introducing the orange curves. The orange curves are our prediction for the correction for the Reynolds number. And actually, you can see that they greatly match what you observe in the experiment. And the good news is that before you had prediction for for beta, the right hand plot, the plot on the right, that go very well from almost Reynolds number 1 to Reynolds number 10 to the 4. But you really have not very good results for the prefactor alpha. Now on the left-hand side, you have excellent results. I will say that they go even a little bit further than Reynolds number equal to 1. So that is a very good news, because now it means that if you have a drop impact and you want to know what will be the force that will be exerted by it, then you can have a good prediction based on experimental results and also theoretical results. Okay, but we also thought about what could be done next, right? We already understand well what happens at the very beginning. We have these square root of time laws that describe well the experiments. But then probably what you are interested more when you have something hitting you is not how fast it grows. It's actually what is the maximal force, right? So this is summarized in this yellow picture, right? And then we plotted what will be the maximal force. This is you can see there the data points on the right. And also, again, we plotted now at which time this maximal force is attained, right? This is something that we already knew. The larger the Reynolds number, the longer is let's say the slower is the impact. So that means that the tau max, the time at which the maximal force is attained, then it's happening it's longer, right? And this is something that you can see on the left. And the thicker is the drop, then the larger is the force. We have also some kind of asymptotic values apparently. Okay. And it's nice because if someone asks you at what time will the drop will have its maximal force, it seems that the larger the Reynolds number, we are approaching the 0.18 value or 0.17, something around that, which is the point at which the maximal force is attained. Okay, and then the question was, can we make some predictions about this? Okay, and then we had a very simple model for this. So this is the picture that I showed you at the beginning, right? Numerical simulations. And we have this front that is going up, okay? We know that the pressure is behaving like this. And now we have that if we can compute the isobars for this drop, okay? Let's imagine that there is a constant pressure thing that is going up. We can compute where is it? And what we observe is that for a given pressure, then the isobar will behave like this. Right, it will go up as a power law of 1 to 1/4, right? And what happens when this isobar meets the top? You can imagine this front is going up, and at some point there is no more drop, right? And if there is no more drop, there is no more momentum to put into the system, and then of course my force has to start to decrease, right? So this is the main idea. This is a competition between the upper part of the drop going down with ballistic motion, okay? And the lower part of this front that is going up, that this has this isobar law that we already found the formula, is going up, and then we want to know when these two match, and when these find each other. When these two find each other, then our maximum force should be attained. And this is what we have in this equation on the left. And then we also have another extra information that we know that after the impact, all the momentum has been consumed, right? And then we can do this very simple, first year undergrad students approach, right? All the momentum of the drop is being consumed by the impact. So that means that since all the drops have exactly the same speed and the same mass, right? Then the momentum consumed should be the same. And then the maximum force, the integral of the force should be the same. And that could somehow be approached by the maximum force multiplied by the time at which this is produced, right? This is classical impulse-momentum balance. When you plug this, and you do it for finite Reynolds number, and now we have that the isobar, this front that is going up now is going a little bit faster. We already know that. And this is happening because we have this extra viscous boundary layer on the bottom. Then this should add some correction. And then our final equation is given by this, right? This is balancing, or this is finding at which point our isobar going up is going to find the upper part of the drop going down. When we do that, we have these incredibly good results again. These are the red curves that we plotted. This is just solving that equation. And the very nice thing is that this is probably the most interesting thing when you are when you care about impact, right? What is the maximum force? And this is something that it has not been done. It was not done before we did this work. So I think this is almost the final result, and I will go through the conclusions. So first, experiments. Okay, what we did for the experiments, we have a very large set of measurements of the normal force exerted by an impacting drop. This somehow is giving the thumbs up to the theoretical results that were done before for the inviscid case. Okay, now we are having nice results, including many different viscosities, and then we have a very nice characterization of the early stage using these 4 sensors. We found this power law that is in agreement with what was proposed by the theory. We also have these maximum force measurements, which are pretty practical, for engineering applications, and we already made that. We also have this practical observation of the Reynolds threshold for inertial behavior. So this is also very important, right? When someone asks you, okay, when a drop that is viscous can be considered as an invasive drop, right? You want to know where is that threshold. And we already found that. This is more or less Reynolds 1. Then I will go back into that, probably with someone that is a good observer may have realized about that. There is also the observation of viscoelastic effect for a very high Reynolds number. Okay, I will leave that without going into details, hoping that someone asks us about that. Then concerning the theory, what do we have as contribution? We have a theoretical model for these nested boundary layers. These have a viscous and inertial boundary layer that is developing in the place where the drop hits the surface. That will have, and this is something that we found, a feedback on the bulk of the second order. This is something that we did. It was not still done by the French group. And the good thing about this is that we found that the behavior is exactly the same power law. It's again still going as a square root of time, but is adding an increasing celerity for the inertial front. So basically, this is saying that when you have a viscous drop, the main difference is that this pressure front is going faster than when you don't have when the viscosity is lower. Finally, we have this nice law for the Reynolds dependence at early times, which is quite practical also for engineering use, right? And also we have this first full model that describes maximum force and time with a very simple idea, right? Just this competition or this race between the pressure front going from down, right? Trying to hit going upside, expanding because of the impact, and also the ballistic motion of the upper interface that is going down. And actually this describes very well what is observed in experiments. Okay, so if you're interested in our work, and this is a very, I think it was a very complete work that we did in 2018. It has been very cited in the last year, in the last 2 years, and we are also still making some measurements with think Pisu, because now our our next um, our next interested is to find what happens with the shear force, right? All these measurements were done to understand the normal force, which, if you want to know how hard a drop hits, is of course very important. But in many physical processes, what is interesting is also the shear force, right? You can imagine, if we go back to these experiments of drops on the sand, you can imagine that the crater actually is not only formed by the normal force of the drop, but also by the ability of the drop to take away material from the center, right? And that will be related to the shear force. So Timpi is in the University of Minnesota is developing this other new set of experiments where now he is measuring the shear force. And that will be very important, for erosion processes or for carving processes using liquid droplets. And we hope also that it may give us some interesting results about crater formation in planets too. Okay, so that will be the end. So thanks again for the organizers for this nice invitation, and I hope that you have some interesting thoughts after this presentation. Okay.
Thank you very much, Leonardo, for your nice talk. We have some time, then we have time for questions. I will ask Geraldine to help us in the questions.
Great.
Profesor, tenemos el siguiente comentario y preguntas. Estos fenómenos tienen varias aplicaciones en la ingeniería. Una aplicación muy importante está relacionando la interacción de líquidos a alta temperatura impactando con sólidos granulares de geometrías complexas. ¿Podría darnos su percepción sobre los métodos más prometedores para abordar este problema? Con demandas de capacidad computacional razonables para procesamiento multicore.
Okay, that's actually a very good question. So the first thing is that a few months ago we received this. There was a publication that was done, made a little bit based on many of our results that is related to what happens when you have. It was very engineering problem. I never thought that someone could be, studying these kind of things. But there was someone interested in what happens when an engine of an airplane is passing through these areas where there are volcanic ashes. And when you have volcanic ashes, many of these impacts are happening at very high speed, high Reynolds number, and all these ashes can be somehow considered as liquid droplets. And this is something that I saw very recently. And the question is, what will be my opinion in studying interaction with some complex materials? Okay, I think that it was a good thing that we did this before that, because usually when you do a physics problem, usually you want to start with a simpler problem. I think that now that we understand a lot of things about how this force grows in time, about how is the maximum force is attained, now we have a little bit more of tools to predict what happens when you are dealing with another material, like granular matter or any other kind of material, right? Actually, what ThinkP is doing in Minnesota for measuring the shear force is making this droplet interact with a soft substrate, right? But this is like not a rigid substrate, but something that can be deformed, so then it can be stretched when the drop impacts, right? So the thing that I will say is that, by the way, I have also seen works when they aiming to understand what happens when you have interaction with grains and the shear force. They made these numerical simulations also to aim to understand what is the shear force. I will say that definitely numerical simulations are very important. I mean, I will say that in this problem that is much simpler than dealing with complex materials, I will say that the contribution of numerical simulation was a key to find self-similar behavior, and is the self-similar behavior that finally is giving you the predictions for the force. So I will say that the first approach, doesn't matter which kind of complex material, whether the drop, whether the substrate you are using, should be numerical simulations. And I think that there are some keys that can be obtained from our results. For example, now that we know what is the time at which usually an interaction is happening, then you can use these in order to decrease the cost of your computations, right? Or you can also aim to make things compete, right? You know that there is some time scale related to the impact, and you may be using a material that has some other time scale related, and probably the interesting things will happen when these two time scales are close to each other, right? If you use a material that has a very short time scale, then it will mainly be seen as a solid by the drop. And I don't know. So probably you can get some key ideas from this. So that will be my recommendation. Like, okay, yeah, numerical simulation will be the key, of course. It will give you a lot of information. But probably if you don't want to make like a blind search, then probably you still want to see a little bit of the theory in order to find which is the interesting thing.
Obrigada, profesor. Y otra pregunta, ¿usted cree que la aproximación de viscosidad infinita es razonable?
Well, I think this is probably the main result of this. I mean, I can show you back this figure, right? I will say that in terms of the first behavior, right, this square root of time law that happens at the very beginning, I will say that the approximation of a large Reynolds number, that means non-viscosity, at least for the exponent, is pretty good even for Reynolds number of order 1. Okay, Reynolds number of order 1 is pretty thick. Okay, so this is amazing, right? Because this means that your drop can be pretty thick, but still somehow behaves as a non-viscous liquid, right? This is related with the exponent. Now, if you want to see the prefactor, and we know the thicker drops hit harder, right? And this is something that you already have seen the results. And you want to see the prefactor, then you will say that probably the approximation is good. Maybe from one Reynolds number something somewhere between 100 and 1000, right? Then the implicit approximation is really is the black dotted curve here. So that means these values are not far from there. But then if you want to go to Reynolds number 1, I will say then that for Reynolds number 1, for the prefactor, the approximation is not any more good. So probably if you are maybe paintings, right? If you want to paint something and you want to study what will be the impact force of this drop and you know the viscosity, these figures could give you a good idea to assess if you want to assume the an infinite Reynolds number or not.
Certo, professor. Também tinha mais uma adicional à pergunta anterior sobre a transição de fase em contato sólido-líquido. Qual que seria sua opinião?
Well, that's a pretty tough question. I mean, still we have to come back to here, right? I guess to what happens with this transition. We still don't have the answer about that. I mean, we know that basically because this means interaction with the solid bed. I think that we made a big step understanding, what are the forces related to the liquid, and at some point we thought that if we could understand well the force, then we could probably have some further ideas about how to understand this transition, which is probably the most interesting thing of the whole picture, right, concerning crater formation. But we still don't have the answer. I think that this is something that probably someone wants to do as a PhD thesis or a postdoc, right? It's a very, very complex problem still to go through, and I think that it needs deeply understanding of how craters are formed, well beyond understanding what is the solid that has been very studied, right? What happens when we throw just a solid sphere on a crater, or what happens when we just throw a liquid in the high Reynolds number limit to a crater. I think that there are still so many things to answer there, so we still don't have the answer.
Bueno, parece que terminamos con las preguntas. Muchas gracias, profesor.
Yeah, I'm really, really impressed about the good questions that you did. I'm really happy of having this talk. So if you have any further question, or we can you want to discuss further, so please, here is my email. So I will be happy to answer to you.
Yeah, maybe Professor Castro can contact you for more discussion.
Great.
And if you can, I see your email in the presentation. Can we see?
Yeah, it's here, right in the last. Can you see there?
Yeah. If we have more question, we can contact you by email.
I will be very happy to answer any question if you have.
Yes, here we can see better the email in the screen.
Great.
And congratulations, Leonardo, for the nice research, for the nice paper you show us. And also, again, we thank you for the nice nice conversation that we have here.
Okay, you're welcome.
Thank you again for the participation.
Thank you very much. You're welcome.
Okay, welcome. You are welcome. Bye.
Bye.
Eu agradeço, então, mais uma vez aos participantes dessa conferência. E agora a gente vai ter um intervalo entre meio-dia e 14 horas para o almoço, e as palestras retornarão às 14 horas. Então, a gente fica por aqui.